let us start with unit C17, that is aldehydes, ketones, carboxylic acids and compounds containing nitrogen. So let us start with first question. Which of the following statements regarding aldehydes is not correct? First, addition reactions occurring across C double bond O is electrophilic type. Now C double bond O in carbonyl compounds has carbon atom which is electrophilic in nature, and because the carbon atom is electrophilic, so whenever there is an addition reaction, usually it will attract a nucleophile towards itself, and when this nucleophile approaches this carbon, double bond will shift. As a result, the addition reactions in carbonyl compounds are of nucleophilic type. Hence, addition reactions across C double bond O are nucleophilic addition reactions and not electrophilic addition reactions. So first option is not correct, and that is the answer 1. That is, it is an incorrect statement. The remaining three statements, that is addition reactions occurring across C double bond O is nucleophilic type, it is correct. Aldehydes undergo addition reactions more readily than ketones, that is also correct, because in case of aldehydes, RC double bond OH and RC double bond OR. Aldehydes have carbonyl carbon attached only one alkyl group which show plus I effect, whereas ketones, they have two alkyl groups which show you 2 plus I effect. As a result, due to plus I effect in case of ketones, carbonyl carbon is less electrophilic. As a result, the reactions undergoing shown by aldehydes are more easily than compared to ketones. Therefore, third option is also correct. Fourth one says addition reaction shown by C double bond O group is catalyzed by acids. That is also correct, because the oxygen attached to carbonyl carbon gets easily protonated in acidic medium. Hence, it facilitates the reaction more easily. Therefore, fourth statement is also correct. Let us go to question number 2. It says, which of the following has the most acidic hydrogen? Options are 3-hexanone, 2,4-hexane dione, 2,5-hexane dione and 2,3-hexane dione. To decide the compound having most acidic hydrogen, we have to look into their structures. So let us see their structures. First one is 3-hexanone. So I have CH3, CH2, C double bond O, CH2, CH2, CH3. Second compound is 2,4-hexane dione. So it is CH3, CH, C double bond O, CH2, C double bond O, CH2, CH3. Third one is 2,5-hexane dione. So it is CH3, C double bond O, CH2, CH2, C double bond O, CH3, and fourth is 2,3-hexane dione. So CH3, C double bond O, C double bond O, CH2, CH2, CH3. Now, since all the four compounds are carbonyl compounds, we know that alpha hydrogen, that is hydrogen attached to carbon which is directly attached to C double bond O group, is acidic. All of them are having acidic hydrogen, but most acidic hydrogen can be observed in case of compound 2, where the CH2 group is situated between two carbonyl groups. As a result, this carbon has most acidic hydrogen. Hence, the answer for this question is option. Let us go to question number 3. It says that which of the following will be most easily dehydrated in acidic condition? The options are 4-hydroxypentan 2-one, 2-pentanol, 3-hydroxypentan 2-one and 5-hydroxyhexane 2-one. So to observe the most acidic or the most easily dehydrated molecule, we have to see their structure. So let us go for the first 4-hydroxypentan 2-one. It is CH3, C double bond O, CH2, COH, CH, CH3. Second one is 2-pentanol. So it is CH3, CH, OH, CH2, CH2, CH3. Third is 3-hydroxypentan 2-one. So it is CH3, C double bond O, CH, OH, CH2, CH3. Fourth one is 5-hydroxyhexane 2-one. It is CH3, C double bond O, CH2, CH2, CH, OH, CH3. Now, for dehydration in acidic condition, the first step is protonation of OH group. After protonation, OH group will leave and simultaneously from the neighboring carbon, a hydrogen has to be removed. Now, this dehydration will take place in case of that molecule where hydrogen removed in the second step is more acidic. For that, when I look at the molecules, I observe that first option has presence of a molecule having 2 alpha hydrogens. One is this and another is this. When I look at the position over here, I observe that this is highly acidic condition, and in addition to that, after protonation of OH, water will be removed and the second step will easily release a proton because this alpha hydrogen is present exactly next to the carbonyl carbon. Hence, the removal of water is easier over here. In case of the remaining molecules, we observe that OH group which is present can be protonated, but the removal of hydrogen from the carbon, neighboring carbon, cannot be easily facilitated by presence of C double bond O group. Hence, the best option for this question is answer 1, first one. Question number 4. Which of the following will react with water? Options are chloroform, trichloroacetaldehyde, tetrachloromethane and 1,2 ethylene dichloride. Now, out of the 4 compounds, chloroform, carbon tetrachloride and dichloroethene, all of them are organic compounds, haloalkanes, which do not react with water easily. We are left with option 2, that is trichloroacetaldehyde. It is also called as chloral, and chloral reacts with water to form chloral hydrate. So I have trichloroacetaldehyde. I am writing it in expanded form, and in presence of water it undergoes nucleophilic addition reaction resulting in formation of chloral hydrate due to nucleophilic addition in this manner. You have OH, which is linking with to the hydrogen and the electronegative atom, and the resulting structure formed is called as chloral hydrate. So the option or answer is second. Question number 5. The correct order of reactivity of PHMgBr, that is phenyl magnesium bromide, with benzophenone, PHCOPH, CH3CHO, that is acetaldehyde, and CH3COCH3, that is acetone. So they have asked us reactivity of Grignard's reagent with the given compounds. All three of them are carbonyl compounds. The options given to us are in the order as given. Now remember that when we are talking about carbonyl compounds, and we are talking about reaction with phenyl magnesium bromide. Definitely this is going to be nucleophilic addition reaction, and in this phenyl group, which is nucleophile, has to attack the carbonyl carbon. Now remember that reactivity of the carbonyl compounds is judged by steric factors. So when you look at the compounds given to you all, they are PH, C double bond O, PH. Then we have CH3, C double bond O, H. And the third is acetone, CH3, C double bond O, CH3. And from our knowledge about aldehydes and ketones, we have learned that nucleophilic addition is judged by the steric factors, and we talk about steric factors, then most easily available is acetaldehyde, then comes acetone, and then comes benzophenone. Hence, accordingly, when I talk about reactivity, then option second is the best suited for this reaction. So answer is option second. Next, question number 6. The reduction of CH2 double bond CHO by zinc mercury amalgam in HCl and hydrazine in basic medium respectively yield. Alright. Now options are CH2, CH3, that is propene and propene. Second is propanaldehyde and alkane, that is propane. Third option is propane and propene, and fourth option is propanaldehyde in both the cases. Now remember that both zinc amalgam in HCl, that is acidic medium, and hydrazine in basic medium, both are reducing agent, but zinc amalgam in acidic medium reduces both carbonyl carbon double bond and carbon carbon double bond. Hence, when we carry out reduction of the given compound in presence of zinc amalgam in acidic medium, it reduces both C double bond O as well as carbon carbon double bond, resulting in formation of alkane, that is propane. But the same starting material, when you are reducing with hydrazine in basic medium, it reduces only carbonyl carbon. As a result, the product is going to be CH2CH3. That means it is giving me propane. Hence, the answer for this question is option 3rd. Question number 7. The reagent that can be used to convert butane 2-one to propanoic acid is. The options given to us are sodium hydroxide, sodium iodide in acidic medium, Fehling solution, Toland's reagent, and 4th is sodium hydroxide iodine in acidic medium. Now, for us, we have to convert butane 2-one. CH3, C double bond O, CH2, CH3. And we want to convert it into propanoic acid. So propanoic acid is CH3, CH2, COOH. If you observe the molecules, the product, we find that the product has 1 carbon atom less. That means it's a step down reaction. And we are finding out that C double bond O has been oxidized to COOH. If you observe the reaction carefully, the situation is very close to type of haloform reaction, and here we have a situation where I have CH3 group directly attached to C double bond O, which can undergo haloform reaction. And for haloform reaction, the reagent needed is sodium hydroxide with halogen. For us, we have been provided with a situation where we have iodine and then followed by acid hydrolysis. So this is the best reagent which can give me the desired product, because after haloform reaction, the CH3 C double bond O breaks to give us iodoform CHI3, whereas C double bond O is converted into COONA. We add sodium salt, and acidic medium, because of presence of acidic medium, it is converted into sodium into acid. So the answer for the question is option 4th. Question number 8. The reaction C6H5COC6H5, that's benzophenone, with NH2OH, that's hydroxylamine, gives A, which further reacts with PCl5 gives B. The product B is, and the options have been given as C6H5 twice CH double bond NHOH, that's an oxime. Then we have substituted amide C6H5 C double bond O NH C6H5. Third is C6H5 twice C double bond NH, that is imine, and C6H5 CHOH NH C6H5, that is a substituted amine. Now let us see the reaction. I have first step, we have C6H5 C double bond O C6H5 with NH2OH hydroxylamine. The first step that we know is it is going to give us an oxime. Double bond NOH. But the next step of the reaction is reaction with PCl5, and PCl5 will bring about replacement of OH. It will get converted into C6H5 double bond N Cl. Now this situation in presence of acidic medium will undergo some changes in this manner, where Cl leaves, and on further hydrolysis, this will get converted into, because of presence of water, it will get converted and there will be shift of a phenyl group. I will be getting the final product as C double bond O N C6 C C6H5 C double bond O NH C6H5. Hence the final product is option second, that is N substituted, N-phenyl benzamide. Option is answer is second. Question number 9. The Cannizaro's reaction is not given by. Options are: first, trimethyl acetaldehyde, second is benzaldehyde, third is acetaldehyde, and fourth is formaldehyde. Now we all know that Cannizaro's reaction is shown by compounds which do not have presence of alpha hydrogen. If we look at the options, we find first option is trimethyl acetaldehyde, which is CH3 thrice C, C double bond O, H. Second is benzaldehyde, that is benzene ring with C double bond O, H. Third is acetaldehyde, that is CH3 C double bond O, H. And fourth is formaldehyde, H C double bond O, H. Now the question is, which one does not give Cannizaro's reaction? So for that we have to look for option which has alpha hydrogen, and from the options we observe that third, acetaldehyde, has presence of alpha hydrogen, hence it does not have tendency of undergoing Cannizaro's reaction. Hence the answer in this case is third. Remaining three of them do not have presence of alpha hydrogen, hence they can undergo Cannizaro's reaction. Question number 10. M-chlorobenzaldehyde on reaction with concentrated KOH at room temperature gives. Now I have my metachlorobenzaldehyde as follows, and we are making it react with concentrated KOH. When you look at the situation, we find that we are having an aldehyde which does not have presence of alpha hydrogen, and the reagent which is used, it is a strong alkali, which points us that the reaction is talking about Cannizaro's reaction. And this compound on Cannizaro's reaction gives us two products. One is an alcohol, which is the reduction product of the Cannizaro's reaction, and the second one will be potassium salt of acid, which is the oxidized product of Cannizaro's reaction. Hence, if I look at the products, I will have metachlorobenzyl alcohol and I have metachloro, product of sodium benzoate. So for this, the correct option will be answer. Option will be fourth, potassium M-chlorobenzoate and M-chlorobenzyl alcohol. Option is fourth. Question number 11. Which of the following compounds does not undergo aldol condensation? We have four options. Now remember that compounds which undergo aldol condensation have to have presence of alpha hydrogen. So if it is not undergoing aldol condensation, it is telling you that it does not have alpha hydrogen. So I have to look for a molecule which does not have presence of alpha hydrogen. So if we look at the structure of molecules given to us, the first option is C6H5, CH2, CHO. Second one is C6H5, CHO, that is benzaldehyde. Third is CH3, C double bond O, CH3, that is acetone. And fourth is CH3, CH2, C double bond OH, that is propanaldehyde. And out of the 4 options, the only person not having alpha hydrogen is benzaldehyde. Hence the answer is second. Option 2. Next, question number 12. In the reaction pH, CHOH, CHOH, CH3 plus H plus gives B. The compound B is. Now, the reagent that is given to us, or the starting material, is 1,2-diol. pH, CH, OH, CH, OH, CH3, and the reaction has to be carried out in acidic medium. Now, always remember that 1,2-diols can undergo reaction in presence of acidic medium yielding carbonyl compounds, usually aldehydes and ketones. And this reaction is known by the name pinacol-pinacolone rearrangement. Pinacol-pinacolone rearrangement. During the course of reaction, one of the OH groups undergo protonation. Now, the facility of the reaction is decided by the stability of the carbocation which will be formed by removal of water. Now, if we observe, there are 2 sites where protonation can take place. One on OH group of carbon number 2 and OH group of carbon number 1 and carbon number 2. So, we have possibility that there are 2 ways. One is I can get it in this manner, pH, CH, OH2. This is oxonium ion which will be formed, CH, OH, CH3, or it can be pH, CHOH, CHOH twice, CH3. Now, when there are 2 chances, then remember that protonation will take place on that OH group where the carbon which will form carbocation will be more stable. So, if I think about the 2 choices, always remember that if this OH group is removed here, I have possibility of carbocation formed in this manner, pH, CH plus, CH, CH3, which over here, and the one is pH, CHOH, CH, CH3. Now, out of the 2 carbocations, one is benzyl and another is secondary. We have learned that benzyl carbocation is more stable compared to secondary carbocation. This is less stable. As a result, the reaction will preferably go in this direction. The next step will be elimination of a proton from a shift of proton from this carbon to this carbon results in formation of pH, CH2, C, OH, CH3. This is plus. There will be elimination of proton resulting in formation of pH, CH2, C double bond O, CH3. Hence, the answer to the question is option 3rd. Answer is 3rd. This is less stable, hence reaction is less preferred. Next, question number 13. The based catalyzed aldol condensation reaction occurs with option 1 propanol, option 2 benzaldehyde, option 3 2,2,2-trichloroethanol, and option 4th is 2,2-dimethylpropanol. Now, since it is an aldol condensation reaction, it requires a compound or an aldehyde or a ketone which is having presence of alpha hydrogen. So, in the given option, the compound which has presence of alpha hydrogen will be the answer. So, for that we write down the structures. First one is propanol. Propanol is CH3, CH2, C double bond O H. Second one is benzaldehyde. So, it is benzene ring with the CHO. Third one is 2,2,2-trichloroethanol, that is C, Cl, 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 CHO, and fourth one is 2,2-dimethylpropanol. So it is CH3, C, CH3, CHO. So out of the 4 compounds, propanol, that is option 1. Answer is option 1, which has presence of alpha hydrogen, and only it can undergo aldol condensation reaction. Next, question number 14. Among the following compounds, which will not react with acetone to give a product containing C double bond N group? Now, the options given to us are C6H5NH2, that is aniline, CH3 thrice N, that is trimethyl ammonium, trimethylamine. Third is NH2OH, that is hydroxylamine, and fourth one is phenylhydrazine. Now, aldehydes and ketones react with nitrogen compounds, resulting in formation of, they first undergo nucleophilic addition and then they undergo elimination. Hence, it requires that the attacking compound must have presence of hydrogen on the nitrogen atom of the amino compound. In case of first, if I talk about acetone, CH3, C double bond O, CH3, it reacts with aniline. I write aniline as NH2, C6H5 will undergo reaction resulting in formation of CH3, CH3. You can remove a molecule of water from here, giving you N, C6H5 and imine. Next, when acetone reacts with trimethylamine, there is a problem over here because the molecule of amine does not have presence of hydrogen on nitrogen. It will not undergo addition elimination like the previous one. Next, we have acetone when reacts with hydroxylamine. Again, it is having hydrogen present with nitrogen, will be removed as water, and I'll get enzyme as the product, double bond N, OH. And the last, when acetone is made to react with hydrazine, the hydrazine molecule, I write it in this manner, C6H5 NH, NH2, it will undergo reaction between these two, resulting in formation of hydrazone, CH3, CH3, double bond N, NH, C6H5. So out of the 4 options given, the one which will not give you a product containing C double bond N is option 2, that is trimethylamine. So answer is 2. Question number 15. Which of the following compounds exhibit Felling's test? Acetaldehyde, benzaldehyde, acetone, formaldehyde. Now, Felling's test is a test which is usually shown by aldehydes. It is an oxidizing agent and a mild oxidizing agent, hence it is usually answered by aldehydes. Because of that, option third cannot be the answer. So third, C, acetone cannot undergo reaction with Fehling solution. So we are left with 3, acetaldehyde, benzaldehyde and formaldehyde. Always remember that aromatic aldehydes do not react with Fehling solution because for that reaction the C double bond O is directly attached to benzene ring. As a result, because the carbon is more stable, C double bond O carbon is stabilized due to the resonance of benzene ring. As a result, this carbon is less reactive. It cannot be oxidized by mild oxidizing agents like Fehling solution which has presence of copper. Hence, benzaldehyde does not undergo reaction with Fehling solution. Hence, we are left with only 2, that is acetaldehyde and formaldehyde. These two will react with the Fehling solution and answer Fehling's test. Hence, our option is 4th, which has A and D. Answer is 4th, which has A and D. Next, question number 16. Which of the following statements is not correct? First, acetamide on heating with phosphorus pentoxide produces methane nitrile. Second, structural formula of metaformaldehyde is CH2O thrice. Third, benzaldehyde undergoes Cannizaro's reaction whereas acetaldehyde does not. Fourth, reaction of formaldehyde with ammonia produces hexamethylene tetraamine. Now, acetamide on reaction with P2O5. Remember, phosphorus pentoxide is a strong dehydrating agent, and on dehydration, the resulting compound is CH3C triple bond N. CH3C triple bond N is ethane nitrile. Its IUPAC name is ethane nitrile, or you call it as methyl cyanide in common name. The option which is given to us is telling you that the compound is methane nitrile, which is wrong. Hence, first option is wrong. Second option, structural formula of metaformaldehyde. Metaformaldehyde is this compound. Each corner represents a CH2 group attached to oxygen. Hence, you can write its formula as CH2O thrice. Second is correct. Third option says benzaldehyde undergoes Cannizaro's reaction. That is true because benzaldehyde does not have presence of alpha hydrogen, whereas acetaldehyde has alpha hydrogen. It will not undergo Cannizaro's reaction. Option 4, reaction of formaldehyde with ammonia. Formaldehyde is HCHO. When you make it react with ammonia, it undergoes reaction to form CH2 6N4. This compound which is formed is called as hexamethylene tetraamine. Hence, option 4 is also correct. So, the wrong statement is option 1. Answer is 1. Question number 17. Which of the following statements are not correct? First, benzaldehyde undergoes aldol condensation in alkaline medium. Second, hydrazone of aldehydes and ketones are prepared in highly alkaline medium. Third, reaction of CH3MgI with acetone followed by hydrolysis gives secondary butanol. Fourth, part of aldehyde or ketone immediately surrounding carbonyl carbon is flat. Now option 1, benzaldehyde undergoes aldol condensation. It is wrong. Now why it is wrong? Because benzaldehyde does not have alpha hydrogen. As a result, it will not undergo aldol condensation reaction. Second, hydrozones of aldehydes and ketones are prepared in highly alkaline medium. Now, hydrazone is formed by reaction of aldehydes and ketones in presence of hydrazine, NH2, NH2, and this reaction does not require a basic medium. As a result, highly alkaline medium is required is wrong. Second option is wrong. It results in formation of C double bond N, NH, gives you hydrazone. Option number 3, reaction of CH3MgI, that is methyl magnesium iodide, with acetone followed by hydrolysis. CH3 C double bond O CH3 plus CH3MgI on reaction gives me an intermediate where CH3 will attack carbonyl carbon, result in formation of O minus Mgi. On further hydrolysis, it gives you a tertiary alcohol and not secondary alcohol. So option 3rd is wrong. Option 4th, part of acetaldehyde or ketone, aldehyde or ketone immediately surrounding carbonyl carbon is flat. Yes. Now we have our aldehyde or ketone and we have studied that carbonyl carbon is sp2 hybridized. If it is sp2 hybridized, the structure of the carbon is planar, and if it is planar, then the structure immediate to C double bond O is going to be flat, has flat structure. Hence, the correct answer is option 4th. Part of aldehyde or ketone immediately surrounding carbonyl carbon is. Question number 18. Which of the following statements is correct? First, CHO group in benzaldehyde is orthopara directing group. Second, IUPAC name of C6H5CH double bond CH, CHO is 3-phenyl propanol. Third, complete balanced equation of RCHO with Toland's reagent is as given. And fourth, formation of oximes and other ammonia derivative require basic medium for maximum rate. CHO group in benzaldehyde is orthopara directing group. No, we have studied that when C double bond O is directly attached to benzene ring, C double bond O groups are deactivators, and ring deactivators make ortho and para positions electron deficient. Hence, CHO group is meta directing and not ortho para directing. So it is a wrong statement. Second, IUPAC name of C6H5CH double bond CH CHO is, let us see, here position number 3, carbonyl carbon gets first position, hence position number 3 has phenyl group. Hence, according to the rules of nomenclature, the compound will be called as 3-phenyl prop 2-ene 1-al. So it is not propanol. Option 2nd is wrong. Third, complete balanced equation for aldehyde with Toland's reagent is RCHO. Toland's reagent is ammonical silver nitrate solution, so it is Ag NH3 twice plus in basic medium it gives us RCOO minus plus it gives us, water plus twice Ag, and there will be release of ammonia, and option third agrees with it. So it is correct statement. Reaction of aldehydes and ketones with ammonia derivative. If it is talking about oxime, it is reaction with hydroxylamine, and hydroxylamine does not require basic medium for reaction, hence option 4 is also wrong. So out of the 4 options, the correct one is answer third, option third. Haloform reaction may be depicted as follows. RCOCH3 plus A gives intermediate. Further reaction gives RCOO minus plus B. The product is. Now since we are talking about haloform reaction, we know RC double bond O CH3 in presence of NaOH halogen followed by hydrolysis. Of course, this is going to give you an intermediate which on further hydrolysis results in formation of RCOO minus, and the CH3 portion is converted into CHX3, that is, it is going to give you haloform. Hence, accordingly, the answer for this is option third, CHX3. Answer is option third. Next, it says that which of the following orders of acidic strength is correct? The molecules given to us are RCOOH, ROH, HOH and C2H2. That is carboxylic acid, alcohol, water and ethyne. Now, we know that carboxylic acids are strongest organic acids. Hence, if we look at the molecules, the priority of acidic strength will first come with carboxylic acid. Now between alcohol and water, we have, from our knowledge, we have studied that alcohols are weaker acids than water. Hence, accordingly, if I go for priority order, the next person in priority list is water, then comes alcohol, and finally we have ethyne, C2H2, because ethyne will be acidic only in presence of strong alkali metals like sodium, otherwise it is neutral. Hence the acidic strength follows the following order, hence the answer is option 2. Answer is option 2. Question number 21. Acetic acid differs from formic acid in that. First option, acetic acid is stable to heat. Second, formic acid is stable to heat. Third, acetic acid acts as a reducing agent. Fourth, acetic acid shows positive test with Tollens reagent. Now, we have to see how these two differ from each other. So, if you are talking about difference, both acetic acid and formic acid are acids. But when I talk about their thermal stability, acetic acid is stable to heat. A simple notion, we know that it is used as vinegar for cooking purpose, and we know that since it is used in cooking purpose, it can withstand high temperature. It is stable. On the contrary, when I talk about formic acid is unstable to heat. On heating, it decomposes to carbon dioxide, carbon monoxide and water. As a result, option 1, that is acetic acid is stable to heat, is correct. So answer is 1. Which of the following reagent or solution can be used to distinguish between methanoic acid and ethanoic acid? First, Tollens reagent. Second, FeCl3 solution. Third is NaOH solution, and fourth is sodium carbonate solution. Now, methanoic acid is formic acid and ethanoic acid is acetic acid. we have to distinguish between the two. The options given to us are Toland's reagent. Now, Toland's reagent is a reagent which reacts with aldehydes. As a result, when I talk about acetic acid, it is purely acid. It will not react with Toland's reagent. But when I talk about formic acid, it is having two situations. You have a CHO part which is aldehyde, and you have a COOH part which is an acid. And because this particular molecule is having presence of aldehydic group, it reacts with the Toland's reagent. Whereas acetic acid will not react with Toland's reagent, so it can be used to distinguish between methanoic acid and ethanoic acid. All the remaining three, FeCl3, NaOH and sodium carbonate, all three of them will react. Usually carboxylic acids react with FeCl3 solution, resulting in formation of complexes of RCOO thrice Fe type. With NaOH and Na2CO3, both are bases. Carboxylic acids react with NaOH to give you salt and water. Similarly, it reacts with Na2CO3 to give you again salt, water, and there will be liberation of carbon dioxide. So the only reagent which can be used to distinguish between methanoic acid and ethanoic acid is Toland's reagent. Answer is 1, because methanoic acid will react with Toland's reagent, but acetic acid will not react with Toland's reagent. So answer is first. Question number 23. Relative order of esterification of alcohols. Now, when we talk about esterification reaction, then always remember that reactivity of alcohols depends on the type of carbon, and hence when you talk about reactivity of alcohols, always tertiary alcohols react faster than secondary, will be reacting much faster than primary because it involves cleavage of COH bond. So reactivity will be faster in case of tertiary alcohols and slowest in case of primary alcohols. As a result, answer for this question is option 1. Treatment of CH3CH2COOH, that is propanoic acid, with chlorine in presence of phosphorus gives. Now, I have CH3, CH2, COOH. We are going to make it react with phosphorus in presence of chlorine. This indicates Hell-Volhard-Zielinski reaction, which is shown by carboxylic acids which have presence of alpha hydrogen, and this on further treatment with water will bring about substitution at alpha position. The resulting compound will be CH3, CH, Cl, COOH. This is Hell-Volhard-Zielinski reaction. So answer is option 2. Question number 25. Reaction of formic acid with concentrated sulfuric acid gives. Now remember that concentrated sulfuric acid is a strong dehydrating agent, and when it is made to react with formic acid, it will lose a molecule of water, resulting in formation of CO and hydrated sulfuric acid. Hence the answer is option third. Option third. When propanoic acid is treated with aqueous NaHCO3, sodium bicarbonate solution, carbon dioxide is liberated. The carbon of the carbon dioxide comes from, now propanoic acid, CH3, CH2, COOH. It's an acid. When you react it with sodium bicarbonate, it's a base. So acid reacts with base to form salt and water. So I'm going to get CH3, CH2, COO minus, Na plus, and the CO3 from the bicarbonate is released as carbon dioxide with formation of water. So the carbon of carbon dioxide which is released is coming from the bicarbonate carbon. The carbon of carboxylic acid remains intact. So option is answer fourth. Answer is fourth. Next, 27th question. Which of the following reducing agents can be used to reduce RCOOH to RCH2OH? In this, we are expecting carboxylic acids converted to primary alcohols, and this conversion is best brought about by three members. One is lithium aluminium hydride, then you can have diborane B2H6, or you can go for boron compounds in THF followed by hydrolysis, will also give you primary alcohols from carboxylic acid. So based on the options given to us, option fourth, that is fourth option, is the best choice. So option fourth. Next, question number 28. Which of the following dicarboxylic acids give cyclic ketone on heating? Now, for cyclic ketone, options given to us are propane dioic acid, pentane dioic acid, butane dioic acid, and hexane dioic acid. Now on cyclization, it is going to give us a carbonyl compound, a cyclic ketone, and we have studied, our knowledge about cyclic compound tells us that compounds below 4 carbon atoms, 3-4 carbon atoms which are in ring structure, they are unstable. So when we are expecting a ring ketone, then we have to look for a molecule which has larger number of carbon atoms, and the best choice which suits us is option 4, which is hexane dioic acid, or also it is adipic acid, CH2 4 times COOH. When you heat this dioic acid, it will undergo cyclization. It undergoes 2 stages. One is elimination of water molecule, and second is elimination of carbon dioxide. So it undergoes dehydration as well as a decarboxylation, resulting in formation of a 5-membered ketone, that is cyclopentanone. So option for this question is option 4. The answer is 4th option. Question number 29. Benzoyl chloride is prepared from benzoic acid by, first option, chlorine in presence of sunlight, that is HNO. Then we have sulfuryl chloride, SO2Cl2, thionyl chloride, SOCl2, and fourth, chlorine in presence of water. Now conversion of acids to acid chloride can be easily brought about by using thionyl chloride, SOCl2, can be easily brought about by using thionyl chloride, and it is the best way of halogenation, because all the products other than the benzoyl chloride formed will be gaseous in nature and can be removed. So answer for this question is option 3rd. Option 3rd. Which of the following acids has smallest dissociation constant? First is monochloropropanoic acid. Second one is also monochloropropanoic acid, but the position of fluoro groups are different. So let us see the structures. CH3, CH, F, COOH. Then comes a CH2, F, CH2, COOH. Br, CH2, CH2, COOH, and CH3, CH, Br, COOH. Now, since all the four acids have same number of carbon atoms, their acidity is determined by the substituent group present on the acid and the distance of the substituent group from the COOH group. From our knowledge, we know that fluorine is most electronegative. It exerts highest minus I effect. As a result, the fluoro acid will be stronger than bromo acid because bromine is less electronegative. So first two options are stronger acids. They will be having higher dissociation constant. So now we have to decide between option 3 and option 4. In option 3, bromine is present on the third carbon atom, whereas in option 4, bromine is present on the second carbon atom. The acidity of the substituent group, the acidity of the carboxylic acid is affected by distance of substituent group. Hence, when I talk about acidity of 3-bromopropanoic acid and 2-bromopropanoic acid, 3-bromopropanoic acid will be weak compared to 2-bromopropanoic acid because bromine is more closer in case of 2-bromo compound compared to 3-bromo compound. Hence, the smallest dissociation constant will be shown by weakest acid, and weakest acid among the four is option 3rd, that is 3-bromopropanoic acid. Hence, the answer is 3rd. Question number 31. Chlorobenzene can be prepared by reacting aniline with, we have to prepare chlorobenzene, and the starting material given to us is aniline. From our knowledge of amines, we know that aniline can be converted into chlorobenzene, but this requires conversion. The options given to us are hydrochloric acid, cuprous chloride, chlorine in presence of anhydrous AlCl3, nitrous acid followed by heating with cuprous chloride. Now, from our knowledge, we have not learned any reaction of aniline with HCl and CuCl directly. Hence, they cannot be the option. Third option is chlorination in presence of AlCl3. That will bring about ring halogenation, but NH2 remains intact. Our reaction is requiring replacement of NH2 with chlorine, which can be only brought about by making this NH2 group react with NaNO2 in presence of HCl. It will give us diazonium salt, which when treated with chlorine in presence of cuprous chloride, which is Sandmeyer's reaction, which will result in formation of chlorobenzene. Hence, the best option for the following conversion is answer, that is option 4. Answer is option 4. Question number 32. Among the following, most basic compound is: first, benzylamine, second, aniline, third, acetanilide, and fourth is para-nitroaniline. So, to check the basicity, we first need to know the structure of the compounds. So, when I go for benzylamine, it is benzene ring, CH2, NH2. Then is aniline, that is benzene ring directly connected to NH2. Third is acetanilide, that is CH3 C double bond O NH with benzene ring. And fourth is para-nitroaniline. From our knowledge of amines, we have learned that aryl amines, that is NH2 directly attached to benzene ring, they are less basic than alkyl amines. Hence, I leave out the options second and fourth because they are aryl amines. Now, we have two left. One is acetanilide and another is benzylamine. Benzylamine is an aryl alkyl amine. It is an aryl alkyl amine, whereas acetanilide is an amide, and amides are neutral. Hence, the most basic compound in the given option is option 1, that is benzyl amine. So, answer is option 1. Question number 33. Which of the following statements is not correct? Aliphatic amines are stronger bases than ammonia. Second, aromatic amines are stronger bases than ammonia. Third, alkyl group in alkyl ammonium ion more stabilizes the ion relative to amine. Fourth, aryl group in aryl ammonium ion less stabilizes the ion relative to amine. Now, first option, aliphatic amines are stronger bases than ammonia. It is correct because alkyl groups exert plus psi effect, and because of the plus psi effect of the alkyl group, the electron donating ability of the alkyl amines is very strong. Hence, these amines are stronger bases than ammonia. Second option, aromatic amines are stronger bases than ammonia. In aromatic amines, NH2 group is directly attached to benzene ring. And since it is directly attached to benzene ring, we have learned that the lone pair of electrons available on nitrogen are used up by the benzene ring during resonance. Hence, they are not easily available. As a result, they are less basic, whereas option 2 says that it is more basic. Hence, option 2 is not correct. Option 3 says alkyl group in alkyl ammonium ion, it stabilizes the ion relative to amine. Yes, because in case of alkyl group, because of its plus psi effect, the ammonium ion will be stabilized. It will be due to plus I effect. That is true. Whereas, if there is an aryl group attached to the ammonium ion, if it is attached to the ammonium ion, the molecule will not be stabilized because the benzene ring is pulling the electrons due to minus M effect. Therefore, it is less stable. The option 4th is also correct. So, the only incorrect statement in the 4 option is option 2nd. Answer is second. Aromatic amines are stronger bases is a wrong statement. Question number 34. Activation of benzene ring by NH2 group in aniline can be reduced by treating with. Now, activation of NH2 group can be reduced by locking the NH2 group by carrying out acetylation reaction, and for acetylation reaction we usually make it react with acetyl chloride in presence of usually an organic base which blocks the NH2 group in the form of NHCOCH3, that is acetanilide. As a result, the activity is decreased. Hence, the answer for this question is option 4th, acetyl chloride. Question number 35. The number of resonating structures of aryl ammonium ion is. Now, aryl ammonium ion is benzene ring attached to NH3 plus, and since there is no delocalization of electron, so in case of aryl ammonium ion there can be only two resonating structures, that is Kekulé structures. Two resonating Kekulé structures, that is all the structures that we can find in case of aryl ammonium ion. So for that, answer is option 1. You have only two structures possible for aryl ammonium ion. Question number 36. The correct sequence regarding the basic strength of aliphatic amines in gaseous phase. Now always remember that strength of alkyl or aliphatic amines in gaseous phase is determined by only positive inductive effect. More is the number of alkyl groups, greater will be the basic character. As a result, tertiary amines will be the strongest bases in gaseous phase. Then comes secondary amine, then comes primary amine, and finally we have ammonia. Hence, the basicity order for stability of amines or basic strength of amines is answer option 1. Answer is option 1. The decreasing order of basicity of the three isomers of nitroaniline is. Now, three isomers of nitroaniline is orthonitroaniline, metanitroaniline, and paranitroaniline. The basicity of aniline is affected by presence of group attached to the benzene ring. The nitro group is electron withdrawing as well as minus I group. As a result, the basicity will be affected in both due to resonance effect as well as inductive effect. So when I am selecting the basicity order, then in case of meta we can observe only minus I effect. In case of ortho and para isomers, you observe both resonance as well as minus I effect. Hence, when we compare the strengths, meta will be more basic compared to para. Now, both NO2 group in ortho and para position shows resonance effect. Hence, their basicity will be affected by inductive effect. Closer the group to the NH2 group, more will be the minus I effect, and it will affect the basicity. As a result, meta will be strongest, then comes para, and then comes ortho. So answer will be option 3rd. Answer will be option 3rd. Question number 38. Acetamide is treated separately with the following reagents. Which one of these would give methylamine? Now, we have to make acetamide to react with 4 reagents, and the product expected is methylamine. So, let us see the reactions. The reaction is acetamide has to be converted to methanamine. When we observe the reactant and product, we find that the number of carbon atoms have decreased. And if the number of carbon atoms have to be decreased, that means the reagent which has to be used should be capable of taking away a carbon. So if I look at the options, we have been given PCl5, soda lime, NaOH in bromine, and hot concentrated sulfuric acid. Our knowledge of reactions does not allow PCl5 and sulfuric acid to take away carbon directly. So they are not possible. We are left with soda lime and NaOH. Soda lime is NaOH and calcium oxide, which is used in decarboxylation reactions of carboxylic acid salts, whereas the compound which is given to me is an amide, hence I cannot use soda lime. So I'm left with only one option, that is NaOH and bromine, and our knowledge of amines tells us that use of NaOH and bromine is a method for preparation of primary amines under the name Hoffman's bromamide reaction. It gives us primary amine with having less number of carbon atoms than the parent compound. Hence, the best option for the given conversion is option third. So, answer is third option. Question number 39. Carbylamines test is in alcoholic KOH by heating a mixture of. Now, carbylamine test is a test for detection of primary amines, and this primary amine reacts with chloroform in presence of alcoholic KOH. So, the best choice for this question is option third, that is trihalogenated methane is nothing but chloroform, and primary amine, that is RNH2. So, answer is option third. Question number 40. Which of the following reagents can convert benzene diazonium chloride to benzene? Now, benzene diazonium chloride is benzene ring with N2 and X minus. It has to be directly converted to benzene. So, if it has to be directly converted to benzene, that means a proton or a hydrogen must be attached to benzene ring. This is example of reduction. And for reduction, when diazonium salts are either treated with alcohol or acids, especially phosphorus acids, hypophosphorus acids, H2PO2, H3PO2 plus water, it undergoes reduction to give benzene with H3PO3 plus nitrogen. So, the best choice for this is option third. So, answer is option third. Question number 41. Benzene diazonium chloride on reaction with phenol in weakly basic medium gives. Now, the reaction of benzene diazonium chloride with phenol is a coupling reaction, and that too it is an example of electrophilic substitution reaction. So, in basic medium it will undergo reaction to give you para-hydroxyazobenzene. It is an example of coupling reaction. Yeah. So, answer is option second. Option second. Question number 42. Heinsberg reagent is. Now, Heinsberg reagent is one of the reagents used for distinguishing between primary, secondary and tertiary amine, and Heinsberg reagent is nothing but benzene sulfonyl chloride. So, it is, answer is option 3, that is benzene sulfonyl chloride. Next, question number 43. A positive carbylamine test is given by. Now, remember, carbylamine tests are answered by primary amines only. So, to find the appropriate answer, we have to look at the options. First one is NN dimethyl-aniline. NN dimethyl-aniline is, this is NCH3 CH3. Second option is 2,4-dimethyl N-methyl aniline. So it is NHCH3 CH3, then N-methyl O-methyl aniline, and last is P-methyl benzylamine. So I have out of the 4 options, the primary amine is only the 4th option, that is P-methyl benzylamine. Hence the answer is option 4. Question number 44. Parachloroaniline and anilinium hydrochloride can be distinguished by. Now parachloroaniline and anilinium hydrochloride can be easily distinguished by silver nitrate test. Now why silver nitrate test? Anilinium hydrochloride, it is a salt which dissociates to give you anilinium ion and Cl minus ion, which answers silver nitrate test can be detected. Whereas the chlorine which is directly attached to benzene ring does not come into the solution because the bond between carbon and chlorine is strong. So it will not answer silver nitrate test. As a result, AgNO3 can be used to distinguish between parachloroaniline and anilinium hydrochloride salt. So answer is option 3rd. Question number 45. Bromination of aniline produces. Now aniline has NH2 group which is strongly electron donating group. It's a good ring activator. So when it is made to react with bromine, it will undergo substitution reaction at all the active places, resulting in formation of 2,4,6 tribromoaniline. So answer is option 2. Answer is option